Thank you for the nice introduction and for giving us the chance to introduce here our company and our products. We had already talked about wafer sizes like 200 millimeter that Alexander mentioned. Hamid mentioned the thin film lithium niobate material. Carlos mentioned the PIC device manufacturing. And I will introduce a technology for doing the material treatment, so the material processing and the manufacturing of PIC devices. So, and now I hope that, yeah, it switches now. So I think I can skip this slide since everyone here in the auditory knows what we are talking about, photonics integrated circuits. If I would go into details, it would be like carrying oils to Athens or sand to the beach. So I skip this. But allow me to give some first words on scia Systems. Scia Systems is a specialist in film process equipment manufacturing. This equipment is typically based, in our cases, on ion beam processing technology and plasma processing technology. We have customers worldwide. We are existing since 12 years. We are based in Germany, in Chemnitz, and we had a revenue of about 100 million last year. Our main markets are in MEMS, especially in the RF filter manufacturing business for the mobile communication. We have markets in augmented reality and in high-end optics. Words like EUV lithography optics come into the game. And we look into this new topic of photonics integrated circuits as well. We have a global sales and service network. And we do a lot of technology and process development in-house. So we do not only sell equipment, we sell complete solutions to the customer. Yeah, what we are talking about, photonics integrated waveguides. The performance of such waveguides typically depend on some properties. We have some requirements. So we have special material, nonlinear optical material, lithium niobate or aluminum nitride, aluminum oxide, all these names already were mentioned. We need to optimize the light transmission in such waveguide material. We need to take care of the dimensions that have to fit to the wavelengths we want to transport over that waveguides. So that brings me to topics like lowest losses for total reflection, lowest absorption, low scattering, and of course, high yield on wafers. And so I have highlighted here two main parameters we are able to control. One is the thickness of such waveguides, and the other one is the structure fidelity. First, I want to switch to the ion beam trimming technology that addresses the thickness adjustment. Short introduction on the principle of ion beam trimming. So imagine you have a wafer, let's say a 200 millimeter wafer with a certain film on it. And the film has a thickness variation. The thickness variation can be pretty low. Here in the example, you have a variation from 368 to 360 nanometers, so just 8 nanometers variation. Sounds pretty smooth, but nevertheless, it may not be sufficient for your application. And therefore, we developed the technology that is called ion beam trimming. In the ion beam trimming, you see it in the schematics. You move a wafer in front of an ion beam source with a focus beam, a broad beam ion source with a focus beam, and you remove material on certain positions. It's a contactless high vacuum process with a very good depth resolution, close to single atom layers. The removal is controlled by local dwell time of the ion beam at a certain wafer position, and the dwell time adjustment is pre-calculated and then transferred into a velocity map for this raster scanning. We can also tilt our substrate to a certain angle to achieve there certain improvements. And finally, what you want to achieve is a very uniform film thickness distribution or property distribution of your devices, if you have already devices on that. Like shown here on the right picture, we improved here in this example the variation of 3 nanometer RMS down to 0.13 nanometer RMS by this ion beam trimming technology. This is one nice example. This can also be applied to waveguide, for instance, for lithium niobate waveguide trimming. Here you do this trimming before you structure the waveguide, so just the bare film material is there trimmed to a certain uniformity. This can be applied for POI wafers, so lithium niobate or lithium tantalate on silicon, for silicon nitride films, for silicon oxide films, or silicon films on silicon oxide, so SOI wafers. All these materials can be trimmed. Even other materials are trimmable with that principle. We achieved their uniformities of 0.1% and better. Here are some nice examples, nice examples of lithium niobate trimming. So you see the pre-data in the left picture with some variation in the thickness, with a standard variation of 3.84 nanometer, and this could be trimmed down to 1.32 nanometer standard deviation with our ion beam trimming process. Also, silicon nitride is a material that can be trimmed. Here's an example of a silicon nitride film of 435 nanometers in average on a 2.5 micron silicon oxide film on a wafer. Here, even the pre and post data comparison. To make it more visible, I have put here also a histogram. So you see in the dark blue distribution, the variation of the thickness over a wide range of 425 to 450 nanometers, while after our ion beam trimming, all the measurement spots are close to the 400 nanometer target thickness. So here are the values. So we decreased the standard deviation from 4.8 nanometer down to 0.3 nanometer, really atomistic level, what we achieved. And I also like to mention here two other properties like the RMS roughness, where we did not see any negative effect. So the roughness pre and post processing stayed the same, 0.3 nanometer. And also the refractive index of that material, of the silicon nitride, stayed the same at a refractive index of 2.023. Post and pre is the same. So we achieved the improvement of the silicon nitride thickness standard deviation by a factor of 16. We did not change the roughness or the refractive index, means no increase in optical losses. And we have there also achieved the losses in the range of 0.14 dB per centimeter in some customer applications, but I cannot show any more detail on this. So here is a tool that is doing this process. It's a 200 millimeter tool, but can also be upgraded to a 300 millimeter tool with fully automatic processing of any film and wafer material. The film thickness correction could be down to 0.1 nanometer RNS. Typically, the processing takes a few minutes. Wafer size up to 300 millimeter, I mentioned already. No edge exclusion, since we have an electrostatic chuck that exposes the full wafer surface to the process. And with that, you can achieve a significant yield improvement, and throughput optimized design with two process chambers is also available for high throughput manufacturing demands. But we have also their R&D versions. We can also apply their technology, is called zero base edge function, to achieve also very, very low corrections with high precision. Then I switch over to our second property we will address with our ion beam technology, the structure fidelity. The structure fidelity, or the structuring itself, it's addressed by ion beam etching. Ion beam etching is similar to the trimming, but here we irradiate the full wafer at once with an ion beam source. The ion beam source is accelerating ions to the surface, and on the surface, the material is sputtered out, is removed, like it is shown here in this diagram on the right upper corner. And we can etch nearly any material as long as it has a sufficient high melting point and is vacuum suitable. Even multi-layer stacks can be easily etched, since the physical etch rate is more or less in the same order of magnitude for all materials. We call it ion beam milling or ion beam etching when we just apply noble gas in the ion beam source. So we hit the surface with noble gas ions like argon. But we can also apply reactive gas in such a process. Then we call it reactive ion beam etching. So we increase the etch rate and some selectivity. And further improvements can be achieved by a so-called chemically assisted ion beam etching. That is a mix of noble ion irradiation plus a chemical substance what is fed close to the substrate, to the surface. For patterning of, for instance, lithium niobate waveguides, we have some requirements like smooth sidewalls, and the sidewalls should be free of redeposition. And therefore, we have a two-step approach. In the first step, we etch perpendicular, means we etch from the top through our mask into the lithium niobate and create there the waveguide while we rotate the substrate, the wafer. And then for keeping the sidewalls clean, we tilt the wafer to a certain angle of, let's say, 70 degrees. And then we hit this side of the structure with an organ beam to clean it up. So, of course, in different times. So the first step is a long etching process, while the second one is just a short cleaning flash. And we apply there a mix of noble gas and reactive gas. So we apply there typically the reactive ion beam etching process flow with CHF3 as a reactive process gas. Here are some examples what can be achieved or what can happen also. We see here in waveguide that should be structured through a photoresist mask with a requirement of 75-degree sidewall angle, or larger than 75-degree sidewall angle, of course with low sidewall roughness and no redeposition. But the challenge here was that the photoresist was thermally unstable, and so the mask reflows and shrinks. What you can see here in this SEM photograph, that the mask doesn't look pretty well. And we developed their process combined by resist bake out plus a very improved cooling during the processing and a partially reactive process, and achieved there a nice etching of a lithium niobate structure. What you can see here in the SEM picture on the lower right side. Yeah, the tool where this happens is the SCIA 200. We have also here the 300 millimeter version available. You see here the picture of the version with 3 process modules and 2 load logs, so high volume manufacturing ready. We can process their wafers with photoresist masks or hard masks. We have good cooling. The etching angle could be adjusted with tiltable and rotatable substrate holder, as mentioned before, up to 300 millimeter. I also mentioned we optimized the system for high throughput with that robot system and multiple modules. And we have also versions as flexible tool for R&D and startup companies with just a single load log available. And this brings me to the summary. Here is a comparison of these 2 technologies once again. So on the left-hand side, the ion beam trimming for this thickness adjustment, and on the right-hand side, the reactive ion beam etching for structuring for this material. And with that, I'd like to thank you. And I'd also like to mention that we are at the Semicon Europe at booth B1470 available. If you like to meet us there, then you can visit us there. Otherwise, you can also drop us a message. And of course, you can ask questions now. Thank you.